Hi there, this is GCSE Physics. This is Particle Model Lesson 6, Specific Latent Heat. So the objectives are to recall the equation for specific latent heat and to apply the equation to solve physical problems. So what is specific latent heat? When heating some ice, we can directly measure the energy increase by measuring the change in temperature. However, during a phase change to water, for example, we cannot, as the temperature is constant. So the energy for a phase change is kind of hidden from us. And latent, the latent heat basically means the hidden heat. Latent is a Latin word which directly translates to being hidden. So latent heat literally translates to hidden heat. Remember to pause at any point if you want to take any notes. Okay, let's move on. So there's an equation that describes this, and it's energy for a state change equals mass multiplied by the specific latent heat. So it's pretty straightforward. E equals ml. Energy is measured in joules, mass is measured in kilograms, and latent heat is measured in joules per kilo. So you want to make sure you've got that down before we move on. A few more notes then. So let's be specific. It's a bit of a rubbish physics joke. First one. So the specific latent heat of fusion, specifically, is the amount of energy required to turn 1 kilogram of a solid into a liquid, or conversely, a liquid into a solid. And then the other one is the specific latent heat of vaporization. That's the amount of energy required to turn 1 kilogram of a liquid into a gas, or conversely, a gas into a liquid. If you struggle to get these down, these definitions, and then I'm going to show you a way that you can kind of remember them in your exam, if you need to. So it involves the equation. Let's have a look at that now. So the equation is E equals ml. So energy is equal to mass multiplied by the specific latent heat, be it of specific latent heat of fusion or vaporization. So we know that energy is measured in joules. We know that mass is always measured in kilograms, in physics anyway. So to get L, if you can't quite remember, you could just rearrange to find L. So L would equal the specific latent heat. We need to get rid of a times M to make L the subject. So to get rid of a times M, we need to divide by M on the other side. So that would be energy divided by mass. And we can look at the units there. So energy is measured in joules divided by mass in kilograms. So latent heat is joules per kilogram. From that, we could write specific latent heat. So just take me a second. You could do this in your exam if that's your definition. So specific latent heat is the amount of energy required to phase change 1 kilogram of a substance. And with the definitions that you've got from earlier, if it asks for fusion, you specifically talk about solid into a liquid or liquid into a solid. If it asks about vaporization, then it's liquid into a gas or gas into a liquid. Specific latent heat, L, is material dependent. So depending on the all the different materials or substances require a different amount of energies to melt or to boil. So for example, water, the specific latent heat fusion of ice or ice to water is 336,000 joules per kilogram. Whereas the specific latent heat of vaporization from water to gas is around 2.25 megajoules per kilogram. I mentioned this in one of the previous lessons that the amount of energy required for vaporization is obviously more than it is for melting. Okay, let's move on. Let's do some questions. So let's pause and have a go at these, and then I'll take through the answers. So the first one, the specific latent heat of fusion for lead is 26,000 joules per kilogram. Calculate the amount of energy required to melt 2,500 grams of lead. So E equals ml. So straightforward, it's mass times latent heat, so it's 2,500 grams, so we have to divide that by 1,000, so that gives us 2.5 kilograms, multiplied by 26,000. Put that in your calculator. That gives us 65,000 joules of energy. Or you could write 65 kilojoules. So look at the next one. Specific latent heat of ice is 2.25 million, but 2,250,000 joules per kilo. 50 megajoules of thermal energy is given to the ice. Calculate the mass of the ice that could be melted. So we've got E equals mR. And what we need to do is rearrange to make mass the subject. So we just need to get rid of a times L. So to get rid of a times L, we need to divide by L on the other side. So that'll be energy divided by L, and that will give us the mass. So we need to do the energy. 50 megajoules is 50 million. So that's 50 with 6 noughts. Or, if you wanted to, you could do 50 times 10 to the 6. Depending, either or. If you do 50 million, that's fine. If you do 50 times 10 to the 6, it's exactly the same. So we're going to divide that by the specific latent heat of fusion, which is 2,250,000 joules per kilo. Put that in a calculator and we get 22.2 kilos. Okay, let's move on to the last one. So the last one, 3.8 megajoules of thermal energy is used to melt 3 kilos of an unknown substance. Calculate the specific latent heats. So this one's E equals mL. So this time we need to rearrange to find L. So we need to get rid of a times M, so we're going to divide by M. So energy divided by mass equals latent heat. So the energy is 3.8 megajoules, so 3,800,000. Or you could have done 3.8 mega being million times 10 to the power of 6. Either or, completely up to you. And then divide either of them by 3. They'll obviously give you the same answer. So the latent heat of fusion, the unknown one, is 1.3 or 1.26, but we're round to 1.3 million, or times 10 to the power of 6 joules per kilogram. Or you could have written 1.3 megajoules per kilogram. Okay, let's move on. Let's do some more questions. So let's start with this word fill. First of all, if you want to pause and have a go, then I'll take you through the answers. So the distance between the particles in steam is something than the distance between the particles in liquid water. So the distance between the particles in steam is greater. Excuse my good handwriting. The density of steam is something than the density of liquid water. So the density of steam is less or lower than the density of liquid water. All right, let's move on. So let's pause and have a go at these, and then I'll take you through the answers. Okay, let's move on. So the first one, name the process that is occurring in region B. That'll be boiling. So it's going from water, B be boiling, then obviously once the water's all boiled, it'd go up again, but obviously in a straight line. Okay, let's have a look at the next one. So what is happening to the temperature at region B? Well, it's constant temperature due to a phase change, so nothing is happening, staying constant. Third one, what is happening to the internal energy at region B? Well, the internal energy would increase. So if you remember, the internal energy, which I'll just write internal there, is equal to the sum of the kinetic energies plus the sum of the potential energies. We covered that a couple of lessons ago. So if at region B we undergo a phase change, so internal energy will increase. What is happening to the kinetic energy at region B? Nothing. If you remember rightly from a couple of lessons ago, kinetic energy only increases when there's a change in temperature. So in this region, the kinetic energy would increase, whereas at B, the kinetic energy would remain constant. What is happening to the potential energy at region B? Increasing. When there's a phase change, it's the potential energy that increases. We covered that a couple of lessons ago as well. Okay, last one, quick calculation. So how much energy is needed? Well, energy is mass times latent heat. So we simply need to do the mass of 1,500 grams. So we need to divide that by 1,000 to turn it to kilograms. So 1.5 multiplied by the 2.26 megajoules, so that's 2,260,000. Or, because it's mega, which means million, you could write 2.26 times 10 to the power of 6, which is the same thing. I've just multiplied it. You can multiply it by a million on your calculator and it'll probably give you that number anyway. And then just times that by the mass. So that will give you an energy of 3.39 or 3.4 megajoules, or 3.4 million joules. Hopefully you found that okay. Thanks for watching, and I'll speak to you soon.